Here's an example of an integral where we're going to do partial fractions and eventually we're going to have a quadratic factor. Alright, so first of all, let's figure out what this denominator is equal to. Let's try to break it up using partial fractions. First of all, we would want to factor the denominator. We could factor out an x. But there's really no other way to factor that. X squared plus 2 is not factorable. It's an irreducible quadratic. So according to partial fractions, it's going to be something over x plus something over x squared plus 2. I can use the cover-up method to figure out what goes above the x, so let's go ahead and do that. Let's cover up the x. Let's plug in x equals 0. If I plug in x equals 0, I'd have 1 over 0 plus 2, so that's 1 over 2. Now, the other fraction, we got a quadratic factor, and when you have a quadratic factor, you have a linear top. Okay, linear top, so linear means you got x to the first power, so it's going to look something like ax plus b. Alright, what we're going to do to solve for a and b is we are going to multiply both sides by that denominator, x times x squared plus 2. The left-hand side would just be 1. The right-hand side would be 1/2 times x squared plus 2 plus ax plus b times x. Alright, now what we're going to do, we're going to actually multiply this out. We're going to distribute the 1/2, we're going to distribute the x. And then we're going to combine like terms. Okay, we have a 1/2 x and also we have a 1/2 x squared and an ax squared. So that's the same as a plus a half x squared. We also have a bx, and then we also have a plus 1. Okay. Now the right-hand side looks like a quadratic, right? We got an x squared and an x term. The left-hand side doesn't really look like a quadratic, but I could make it look like a quadratic. I could insert a 0x squared and a 0x if I wanted to. And I do want to. Because what I'm going to do here is I'm going to use a technique I call comparing coefficients. All right. Notice that on the right-hand side I have a plus a half x squared. On the left-hand side I have 0x squared. The only way that these two functions are equal for every single value of x is if every coefficient matches up. So that must mean that a plus a half must be equal to 0. So that means that a is negative a half. Similarly, on the left side I have 0x. On the right side I got bx. That must mean that b equals 0. Notice that both of them have a constant term of 1. That's good. That basically means that we did the cover-up method correctly. Alright, so now we know a and b. And so now we can plug those in and actually do our integral. The integral, our original integral, is going to be broken up into two different integrals. You're going to have 1/2 integral of 1 over x dx, and then plus an integral, I'm going to have negative 1/2 x plus 0 over x squared plus 2 dx. Okay. The first one's easy, it's just natural log x. The second one, what I'll do is I'll factor out, the fact that the b was 0 does make this a little bit easier. I'm going to factor out that negative a half. And then I am going to do a u substitution. I'm going to let u equal the bottom. U is going to be x squared plus 2. Du would be 2x dx, which means that x dx would be a half du. And see, that's going to work because we actually have x dx in our problem. That's going to become a half du when we do our substitution. So I'm going to have a half natural log x. I'm going to have minus, and then yeah, let's go ahead and I'm going to have a u in the bottom, and then I'm going to have just a half I'm going to have a half du in there also. The half du is the same as the x dx. And see, that makes this integral doable because now it's just 1 over u. So let's see, we got, I can factor out that half. A half times a half is a fourth. And this is just going to be natural log u, and the u is x squared plus 2. So there's an example of using, of what happens when you have a quadratic factor in the bottom. When you have a quadratic factor in the bottom, partial fraction says it's going to be some linear function over that quadratic factor. You solve for a and b, first of all, by clearing the fractions. And I chose to do it by multiplying it out and then comparing coefficients. Right? I compared the x squared terms, I compared the x terms, I compared the constant terms. Technically, that'll always give you 3 equations, which is more than enough to to solve for just in this case the 2 unknowns. Okay, but you'll always have enough equations to solve for your unknowns that way.